last 3 years in cooperation with both the City of Steamboat Springs and the Trident Pioneers Museum. And I want to acknowledge my collaborator Jeff Pepin, who's not here today, but we've equally shared in this work. So I'm going to be talking about the mineral springs as subsurface windows to the past and how we are gaining a greater understanding of the hydrogeology of the area of Steamboat Springs. This presentation, I'll start with the impetus for this current hydrogeologic study of the springs, why we're here, and what we hope to do with this. And then I'll provide a bit of background in the previous scientific studies that have been done, which is surprisingly not many. When I started on this project about 4 years ago, I figured that I would have a lot of reading material to dive into, and there's like 3 studies over the course of 150 years on an area that's so important to the state of Colorado and is very unique in its hydrogeology, so that's really surprising. So because there were relatively few previous studies, we have relatively many remaining questions that we were looking to answer. We'll talk about the techniques that we use to study groundwater flow paths in the area around Steamboat Springs and understand the susceptibility to change of some of the springs around town. And then I'll go through the results of our study to date, starting with the distribution of springs along the Yampa River, how many there are, where they're located. Scientific jargony term here, continuous data sets means a sensor that's placed in the spring that measures something about the spring every hour. So I'll talk about how we use those continuous data to understand the susceptibility of springs to change. I'll talk about groundwater age in the springs, which is my personally favorite and most interesting thing that we learned from this study. And then I'll talk about how geologic structures help to shape where the groundwater enters the aquifer and where it exits at the springs that we see in downtown. So when I refer to geologic structures throughout the talk, I'm generally talking about a fault. So the San Andreas Fault, it's probably the fault system that most people know about in the room. So a fault is where there's a brittle break in the Earth's crust. So rocks are moving along one another. There's an offset across the fault plane. So it's essentially a very large fracture. And in deep groundwater systems, water can move along those fractures. And that's one of the things that we found in our study of Steamboat Springs. So to go back to the beginning, talk about the impetus for this study. As I'm sure many people in the room know better than I'm not a Steamboat Springs local, but population growth and urbanization of the area has caused some concerns for human interactions with the geothermal system. So this photo on the left is courtesy of the Trident Pioneers Museum. This is the previous soda spring, and this is actually Highway 40 that is running right there. I'll use my pointer too so folks can see in the back. So this is the gazebo that was over Soda Spring, and this is a plat map that we got from the city. You can see US 40s running right here, and Soda Spring, the gazebo used to be essentially on US 40. It's like the road is encroaching into it. And you compare that to this aerial image of what we see today in Steamboat Springs. Clearly things are very different. So the Soda Spring was unfortunately lost or rerouted during construction of the modern US 40. So when there was construction along the roadway here, there was an attempt to move the Soda Spring gazebo, and after that time, Soda Spring we haven't found exactly where it's going yet. But you can also see some interesting things about the historical map that shows the growth. So there was a cabin and a hotel where there's now the Steamboat Springs Library. And you can see the Steamboat Spring and Narcissus Spring, which is, if you're standing at the library and you look across the river, there's a big travertine mound there that's constantly discharging water into the river. That spring has been known through our study as Narcissus Spring. I believe it may have potentially been known as other names in the past. And then you can see Iron Spring, where we have the current Iron Spring Park. So we can see, just based on this map versus today's walking around in downtown, that many of these springs are probably in around the same place as they were in the early 1900s. but we don't know exactly how many springs there are in the vicinity of the Yampa River because they had some artistic showing of different springs along here, but we don't know if those springs were perennial or if they were seasonal, the temperatures of those springs. So this is one of the things that we wanted to do with our study, is create a map of all the known springs in the area. And in other geothermal areas, detailed geologic and hydrologic studies have been used to understand the sensitivity of geothermal systems to human interactions. And this is an example from Yellowstone National Park, where Old Faithful, probably the most famous geyser on Earth, they were worried about how humans might be interacting with Old Faithful, and if we could, as humans, making changes on the surface or in the shallow subsurface, if we could be changing anything about the geyser. So what they did in this instance is they created a map of the area. So there's Old Faithful right there under the pointer. And they created a red, yellow, and green zoning system. So in the red zone that's shown, kind of looks more like orange on the screen here. In that red zone, that's an area where detailed scientific study indicated that there should be no more surface changes. We shouldn't put parking lots. We shouldn't put power lines. We shouldn't dig up and even maybe only a couple feet down to put a water line or anything, because in the red areas there is hydrothermal plumbing that is probably rooting some of the water around that eventually ends up at Old Faithful. So to be conservative and make sure that we are not interacting with Old Faithful at all, don't do anything in the red zone. The yellow zone is an area where the existing data sets indicated we might be able to do something on the surface. If you wanted to make a new parking lot for how busy Old Faithful is, maybe you could put a parking lot in the yellow zone, but it would require a detailed study of that exact area. So you'd have to go in and collect more data to understand what was going on with the hydrothermal plumbing right in that yellow zone. The green zone, which is only a small portion in the southern portion of the map, that is where existing studies indicated that there's nothing connected to the Old Faithful geyser in that zone of this part of the map. So if we needed a new parking lot or new bathrooms, they could go there and they would not be interacting with the geothermal system. So this is one of the things that from the beginning of our study in Steamboat we had as a potential end goal, is understand where there are areas within downtown Steamboat that are susceptible to human change. So if we can think of a groundwater system as a pipe, very simplified, but I'll be talking about it a couple times today. So we're looking at the downstream end of the pipe. When we're at a spring, we're seeing groundwater discharge. This is some old groundwater, and I'll tell you how old later on. This is water that has spent a substantial amount of time in this hypothetical pipe system. At the front end of that pipe, there's water going in, and that's what maintains the constant discharge of water from the springs. That process of water going into the pipe is called groundwater recharge. So again, going back to the example of Old Faithful, if we're worried about the red zone, that might be because if you were to put pavement over the groundwater recharge zone, the infiltrating snowmelt and rainwater can't get in there anymore. So we essentially just shut off the groundwater recharge to that area. So the goal with Old Faithful study and here in Steamboat Springs as well is to identify the groundwater recharge zones to make sure that we can protect those. Now to talk briefly about just a couple previous studies. Again, there's not much, but the primary impediment to science-based protections for the Steamboat Springs geothermal system is this lack of scientific information. One of the previous studies that was done in the early 1980s looked at mapping ground temperatures and concentrations of helium in the soil. So helium is a noble gas. It's common in, if you've seen those neon signs that light up, neon is another noble gas. So helium is produced by the geothermal system. Now I apologize for this graphic, it's not mine, it's from the 1980s study. But what you can see in the black lines is temperature contours. So you won't be able to read them, I'll just tell you. In the center of this temperature contour, it's about 20 degrees Celsius. and the center of this temperature contour, it's about 18 degrees Celsius. So what these two bullseyes represent is two areas of warm groundwater upwelling that's coming from deep within the surface towards the land surface, and most of the groundwater is discharging in these two zones. So this is the Yampa River, and you can see the grid of the Steamboat Springs streets right here. So this is where Old Town Hot Spring is, and the Sulphur Spring and Steamboat Spring itself are all located in this zone. So based on this 1980s era study, we know that there are two zones of active geothermal activity within downtown Steamboat. In addition to looking at the core of downtown, this study also looked wider afield to understand how Strawberry Park might be connected to the downtown studies. And they used general geochemistry, so they collected water samples and then analyzed what was in the water, and then geologic mapping to identify potential conduits for the flow that was discharging at the springs. So the left-hand map, again, here's the Yampa River. This box is drawn around the town of Steamboat Springs, and all these lines are faults. So that's areas where there's a fracture in the upper Earth's crust, and there's a potential for water flow along those fractures. And Strawberry Park's right here, Old Town's right here, and then all the springs down near the library are right here. So the primary thing that we took away from this is that most of the springs are located near faults, and that is actually what's displayed in the springs pamphlet that was on your chairs. Now the plot on the right, we're not going to go deep into geochemistry here, but the shapes of these different symbols is a general representation of the chemistry of the water from that spring. So they took the water sample, took it to the lab, and these shapes represent the different ions that are in that solution. So the thing to notice is that Sulphur Cave and Steamboat Spring, their symbols are very large. That's because there's a lot of stuff dissolved in them. Heart Spring, which in the 1980s was what Old Town was called, I'm not sure why. Heart Spring.
That's what gives it, that's the source.
Oh, okay.
The source spring is called Heart.
Okay, great, thanks. And then Route Springs A and B, that's what in this report Strawberry Park is called. So the symbols for Old Town and Strawberry Park are very small. There's not very much dissolved in those waters. You can tell that when you walk up to it and smell it. Those two springs are not sulfur smelling. Steamboat and Sulphur Cave Spring are very sulfur smelling. So based on this water quality sampling from the 1980s, we think that there's probably at least two different flow paths that the water takes coming up from the deep subsurface to the surface that would correspond to the different chemistry we see in the waters. So despite these previous studies, various questions remain. Specifically, we wanted to know what the total number of springs are and where they occur. Where does the groundwater enter the system? So again, going back to that idea of the pipe and the recharge zone. How long does it take from that recharge zone to where we see the water come out of the springs? What are the rock units storing the geothermal water? That's also spoken about in the pamphlet. It's got a geologic section in there that shows the different rocks that are found in this area of Steamboat. And then we want to know if all the springs are sourced from the same reservoir, because again, we think that they're probably not, based on the previous studies. So in 2021, the USGS, my employer, initiated this study in cooperation with the town of Steamboat and the Trout Pioneers Museum to answer these remaining questions. And I'll spoiler alert for the end, we won't come up with a map like there was at Yellowstone. We do not yet have red, yellow, and green zones. Yellowstone is the most heavily studied geothermal area on the planet. And here we have 3 studies from the 1980s and now. So we don't have enough information yet to make a zoning map. But this study really serves as the building block to potential future studies that would eventually come up with that zoning map. So I'll talk just briefly about the techniques that we use for understanding the hydrogeology of the springs. we have sensors that measure the temperature and the specific conductance, which is essentially a fancy word for salinity, how much stuff is dissolved in the spring water. We have these at the major named springs down along the river near the library. And these measure temperature and specific conductance once every hour. I just actually decommissioned the last one this morning. So we had about 3 years of hourly measurements from those sites. We measured the discharge rates, how much water is coming out of the springs. That's a good indication of the health of the spring. We use thermal imaging to identify and map all the springs, including very small springs along the Yampa River. And then we used isotopes and environmental tracers. This is kind of a very detailed analysis that we did here that I'm not going to go down into the depths of. I'd be happy to talk to anyone afterwards. But basically we're coming up with the age of the groundwater, how long it takes to travel along that pipe from recharge zone to discharge zone. And then finally we're trying to understand what the temperature is at depth down in the geothermal reservoir and coming up with hypothetical groundwater flow paths that come from that recharge zone down to where we are today. And I really like this schematic. This is not of Steamboat Springs, but I like this schematic, and I'll come back to it again throughout the talk to understand a little bit about how the depth of the groundwater circulation is related to the amount of time it spends in the surface. So this is from an area in Italy that actually has relatively similar geology to the Steamboat Springs area. But you see they've got some mountains up here, and there's a river down in the lowlands with springs discharging on either side of the river. So these arrows are the groundwater flow paths. So up in the mountains, there's a groundwater flow path that starts up and it goes very, very deep, and it discharges multiple valleys away from where it entered the aquifer. And that water would be warm by the time it comes out, as long as it comes up quickly enough to the surface, it would be carrying some of the heat that it gained along that flow path. And so that would be a groundwater that takes a very long time to travel in the subsurface, so we call it quote unquote old groundwater. Now you compare that with, in the center here we have a relatively short flow path that kind of starts at this lake, so you've got a lake that's infiltrating into the subsurface, and then the water's coming out on the spring just on the other side of the hill, essentially. And that would be a short groundwater flow path, and we would call that quote-unquote young groundwater. And we have, using these isotopes, we can actually place direct age estimates on a number of years on how long these different flow paths are. But I like to show this schematic because it helps us to get to thinking about these things in the large scale that we're probably talking about here in Steamboat. So, as I had mentioned, we collect data from the primary named springs along the Yampa, and all of our data are publicly available. So, anyone who'd like, I could send you the link for this webpage and you'd be able to come to the map. You could click on, I've highlighted here, Iron Spring, so you could click into Iron Spring, and then it would come up with a little link here that says Access Data. You could then click into that and you could see the temperature of Iron Spring from yesterday, if you wanted to. So now I'll get into some of our results. I had mentioned that we use thermal imaging cameras to map very small springs along the Yampa River. So there's the 5 primary named springs, Sulphur Spring, Narcissus Spring, Steamboat Spring, so on and so forth. But there are many more springs than that, and you can see them when you're walking under the bridge that's right next to the library there. There's that little spring that's bubbling up out of the cement. That's not one of the main named springs, but it's still important in terms of understanding the health of the geothermal system. So we used the thermal camera to identify these small springs and went out after it had snowed. So the real color image is on the right, and then the thermal image corresponding to it is on the left. And you can see that there's a couple channels here that you could actually identify without the thermal camera. That's where the warm groundwater has melted the snow away. But in addition to those channels, there's an area right along the river bank that shows up as very warm, and you probably wouldn't be able to find that without the thermal camera because it's essentially just an area of hot ground, and if you go and stand there for a long enough time, you can see bubbles forming. And so in mapping all these springs, we collected samples from all of them and noted their temperatures so that we could go back multiple times and look to see if anything was changing with the smaller springs. So this is another photo from our thermal reconnaissance. This is just behind Narcissus Spring along the train tracks. You can see we've got a person was warm on that snowy day, and then all these areas of upwelling are, you can actually see this largest one too. But you wouldn't be able to probably see these two smaller ones or this one along the wall. So there's, if you're walking along the train tracks there, which I think is illegal, so maybe I shouldn't tell you to do that. But if you're walking along the train tracks, there's some discharge coming out of the rocks on your right side, and that's a thermal spring that we mapped using this approach. And then finally, we use the thermal imagery to just make pretty pictures that can go on the website. So this is of Narcissus Spring, and you can identify the main outflow zone, which is coming right through here, and then you can identify some subsidiary outflows that are on the sides of the travertine mound. So when we produce that full map of the springs, we come up with about 26 mapped springs in the vicinity of the river and in Iron Springs Park. And they're shown here with the symbols are colored according to their temperature. Most of them are all around the same temperature along the Yampa River. They're between 19 and 25 degrees C. And then you go across to Iron Spring Park, and they're between 15 and 22 degrees Celsius generally. So just like the 1980s, we saw that there was two areas of geothermal upwelling, one of them centered on Hart Spring, one of them centered on the area of the library. Now that we can see there's actually multiple different upwelling zones within the vicinity of the library in Iron Springs Park. And we did these repeated measurements of all the smaller springs, once in fall and once in winter, because with that large air temperature change, any spring that isn't getting very much groundwater inflow, it would be much, much colder in the winter time. And even though many of these springs are very small, some of them are like a pool about as big as my hands, none of them change temperature substantially between the fall and the winter. So even though they're small pools, they're receiving a substantial amount of geothermal upwelling. And that's good for the health of the system, in that we see that it's relatively consistent through time. Now we'll talk about identifying the susceptibility from daily temperature variations. And this is a graphic from a colleague of mine that I really like, because it helps us to understand how we can use diurnal temperature swings in water to identify if that is receiving no groundwater inflow, shallow groundwater inflow, or deep groundwater inflow. So because we have geothermal springs here, we would suspect most would be deep, but we wanted to use this technique to make sure we had some data to back that up. So if you have I'll talk about the top schematic here. If you have no groundwater inflow into a stream or a pool, then if you measured the water temperature and the air temperature, they would go up about in unison, up and down. You know, it gets hot and cold through the day, through the seasons it gets hot and cold, so you have this sinusoidal pattern. The water temperature would be just a little bit dampened. The highs and lows would come in a little bit from the air. Now if you go to the bottom graphic, the blue squiggly line shows the temperature scenarios in a stream or a pool receiving shallow groundwater inflow. So that's from about the top 15 feet below the surface. If you have groundwater inflowing from that depth, you take the highs and the lows in even more. You dampen the amplitudes of that sinusoidal signal, and then you also shift it a little bit to the right. So you can see this peak is shifted from the air temperature peak. Now, finally, the third possible scenario we have here is deep groundwater inflow, which is the black line. Below about 15 to 30 feet, there's relatively little temperature change in deep groundwater throughout the year. It's almost the same temperature all the time. So when you have deep groundwater inflowing into a stream or a pool, you take those highs and lows way, way down, and you don't have that little shift in the peak anymore. So because we have these temperature sensors that measure hourly temperatures in the springs around downtown, we can do this type of analysis to identify where there's potentially shallower groundwater, because that shallow groundwater is where we have potential for interaction with humans. So many of these springs are by the park. So if there were additional paving next to the park, that could change the recharge there. If there was fertilizer use that could go into the groundwater in the shallow groundwater, that could potentially end up in the spring and change the chemistry of the springs. So when we skip to our data set for this, this type of analysis, what's shown on the y-axis here is the daily temperature change in a single spring. And then the x-axis is just through time. So the spring that changes the most in its daily temperature is Black Sulphur Spring. It changes by 3 degrees Celsius every day during the summertime, and then it goes down to less than 1 degree Celsius up and down in the wintertime. Now compare that with Narcissus Spring, again, right that travertine mound right across from the library. It essentially never changes its temperature. In 3 years of monitoring, one day it changed by 0.5 degree Celsius. And that was probably, my guess is that was a rainstorm. It's probably a very strong rainstorm because of when it occurred in August. So this is showing that Black Sulphur Spring is likely receiving groundwater inflow from some shallow reservoir, and that means that Black Sulphur Spring is more susceptible to human change than Narcissus Spring. I wouldn't want to say that Narcissus Spring couldn't be changed, because the area behind that mound used to be a big travertine mound, and then it was blasted by the railroad, and theoretically that is what turned Steamboat from a geyser into a spring. So humans have a lot of power and responsibility, in that we could probably change Narcissus if we wanted to. I don't know why we would want to, but this is a good indication that Narcissus is relatively stable with its groundwater discharge through time. And then maybe I'll talk about the springs in the middle. Our Steamboat Spring is the next most susceptible to change, and then it's pretty much a tie between Sulphur Spring and Iron Spring. But all 4 of those springs have very little change relative to Black Sulphur.
I would say Black Sulphur changes the most in color,
Mm-hmm.
too.
Yeah, because it changes the color, but depending on, in the spring, isn't it a different color?
Yeah, completely. Yeah. It's not black at all. It's milky.
Mm-hmm. So now I'll skip ahead to my personal favorite part of our study, was the understanding of the groundwater age. So one of the tools that we use to understand groundwater age is tritium. This is a bit abstract, but I'll walk us through it, and then we'll get onto the interesting results that it comes up with. So tritium is a radioactive form of hydrogen, so it's incorporated into water molecules. And it was primarily released during atmospheric nuclear weapons testing in the 1960s. So this is a time series of tritium through time. In 1953, people started blowing up a lot of nuclear weapons in the atmosphere. It released a massive amount of tritium. In 1964, there was a treaty that said we're not going to blow up nuclear weapons in the atmosphere anymore. And so the tritium started coming down since that time to where we are today. So we can essentially use the presence of tritium to indicate if groundwater has been recharged since 1953. Because as rain was falling through the atmosphere when there was a high amount of tritium in it, that tritium entered the water molecule as rain and snow. That water molecule hits the ground, part of it infiltrates into the aquifer, and at that point, the tritium content is locked in, and so then it starts to decay radioactively. But we can backtrack using some calculations to essentially the exact time, to the year, and some people would do it to the month, but I don't know about the accuracy there, to the year when that water fell onto the land surface. And this is getting back to this understanding of this shorter groundwater flow path. So I've blown up that schematic from one of my earlier slides. If we've got a groundwater flow path that comes from this lake and then infiltrates and discharges at a spring just kind of on the other side of the hill, we would expect that that water would have some tritium in it. The very, very deep groundwater we would expect to not have any tritium at all because it predates when atmospheric nuclear testing was conducted. So the results that we see for our springs in Steamboat, this is the tritium activity on the y-axis here, and then these are our different samples. We sampled through time because there's seasonal changes in the mixing in the groundwater system. We essentially can say that most of the groundwater in Steamboat predates 1953. So most of it has no tritium at all. That's what's shown in the blue shading here. No tritium in that groundwater. Sulphur Spring has a little bit of tritium in it seasonally, and so that's showing that seasonally there's a little bit of shallow groundwater that's getting into Sulphur Spring. Black Sulphur Spring always has tritium in it. And so this lines up very closely with the temperature time series that we looked at, where black sulfur has a lot of variation going up and down because it's coming from shallow groundwater. The tritium also indicates that the groundwater in Black Sulphur Spring is relatively young in comparison to all the other springs around town. So again, this is saying Black Sulphur Spring is the most susceptible to human changes. Even though we found a little bit of tritium in some of our waters, most of the groundwater appears to be much older. So for water that's too old for tritium, we use carbon-14. It's the same technique that is used for dating anthropological artifacts, to understand how humans moved throughout North America. We use a very similar technique on the water samples that we collected. And based on the carbon-14 dates, we estimate that the age of the springs range from 2,500 years to 18,000 years old. So Steamboat Spring has the oldest groundwater that we found at just over 18,000 years. And black sulfur, even though it has some of that tritium in it, it's a mixture of young and old groundwater. So there is very old geothermal groundwater that's upwelling underneath black sulfur, and it's also probably getting some inflow of shallower groundwater flow paths along its sides probably. And then the rest of the springs are shown here kind of just in order of increasing age. But I think that the coolest thing about this is that the groundwater ages for Steamboat, Lithia, and Sulphur correspond to the end of glaciation in the Park Range. So the Park Range just to our east here used to be heavily glaciated. This is a map from a report from 1937 where he went around and mapped the extent of glaciers in the Park Range, and Steamboat Springs is right down here next to my cursor. So there was a Fish Creek glacier, came down Fish Creek towards town and didn't quite get into town, at least based on this mapping, but it terminated a little bit to the east of us here. And these ages of Sulphur, Lithia, and Steamboat correspond to when those glaciers were melting. The oldest estimate of glacial melting for the Park Range glaciers is around 22,000 years, shown by the right-hand side of this blue bar. And then that glacial melting was probably complete by about 11,000 years ago. So in that time period, we're going from a very thick sheet of ice to as we see it today, and all that water had to go somewhere. Some of it infiltrated deep into the subsurface and probably became some of the water that we can go and look at across the street. So I think that this is probably the coolest part, the coolest result of our study, is that when you're standing on the little boardwalk at Steamboat Springs, you're partially looking at water that was once in a glacier 18,000 years ago and has made a very long trip between that glacier and now. And the final aspect of our study that I wanted to share with you today is how the geologic structures, those faults, define the groundwater flow paths. In this map, you can see the springs are shown in red, including Strawberry Park, and the purple lines are large faults. So to the east of us in the Park Range, the faults generally go from the northeast to the southwest. You can see these faults in the Fish Creek. This is Fish Creek drainage, so that's where there was that large glacier. the glacier was overlying a large fault which was oriented parallel to the way that the glacier was flowing. Now, there's also a very large fault running essentially north-south right through Steamboat. And so what we believe is that as the glaciers were melting, the faults that were along the bottom of the glacier probably provided a pathway. That fracture is a pathway for the water to flow upon. So the glacier starts to melt, and some of that water would have clearly exited as runoff, and sort of similar to how we have snowmelt runoff today. But a proportion of it at least went into the fault system and probably went deep along that fault. And then the faults are not actually mapped as going all the way to terminating at the northwest fault, but we believe that the groundwater might be flowing from east to west until it hits this north-south fault, and then might be coming up along that fault fracture. So to wrap everything up, the USGS has conducted this integrated hydrologic study over the past 3 years to understand the sources of groundwater recharge and the potential susceptibility of springs to human interaction. And more than 20 smaller springs were now mapped near the Yampa River, and these springs have apparently stable temperatures throughout the year, but we'll be providing the coordinates of these springs to the city and the stakeholders so that they could be monitored going forward, because now that we know where all of them are, someone could go back once a year and check their temperature, and that's a way to look at the maintaining the health of the geothermal system. Oops. And then the daily temperature variation in the larger springs indicates that black sulfur and next Steamboat were the most susceptible to potential human changes on the surface. The groundwater age indicates that groundwater is between 2,500 and 18,000 years old, and that black sulfur also contains some quote-unquote young groundwater on a seasonal, black sulfur always contains young groundwater. Sulfur spring contains young groundwater seasonally. The age of groundwater in the purely old springs, so that's the springs with no modern groundwater, corresponds to the end of the last major ice age, and indicates that maybe glacial meltwater that was traveling deep within the subsurface along faults. And the evaluation of the spring geochemistry and the location with geologic maps really highlights the importance of faulting and fracturing in providing conduits for groundwater flow in this area. And with that, I'd be happy to take any questions. Thanks for listening.
Have you thought at all of how some of the ancient spring systems that are dormant now fit into all this?
That's a really good question, and at the conclusion of our study, which is in about 3 months from now, one of the things that we're going to be providing the city is potential next steps to take, and that is actually one of the next steps that we're going to suggest, because there's travertine is found all along the Yampa River. Thanks. And clearly, Narcissus Spring is the most active area of current travertine deposition, but when you walk up and down the river, you can see lots of travertine mounds, and one of our suggestions is that those mounds could be dated to understand the history of geothermal activity along the river and see if it is moving one direction or another direction, or it appears to be random or stationary. So those are, I don't actually have an answer for that question, but it's one of the things that we'll suggest.
Is this all going to come out in a professional paper? Or?
Yeah.
How do they manage to test for helium or any noble gas that doesn't interact chemically with anything?
The great thing about noble gases is that they have very few interactions, geochemical interactions.
Yeah.
So they're mainly tracers of the physical processes of what's going on in the groundwater. So if you have helium dissolved in groundwater and you allow some of the water to boil off, there's a specific fractionation of the helium that remains. So we use that to trace the subsurface boiling. That was not a thing that I talked about at all today, but the different springs have different
Fractions.
they have different boiling behavior, it appears.
Okay, cool.
Is there a reason why you use Celsius other than Fahrenheit?
Metric's better?
Celsius is metric.
That's true. Celsius is not metric. Kelvin.
Yeah.
Kelvin is metric. I could have used Kelvin. Would anyone know?
I don't know.
Does anyone know the Kelvin conversion?
No.
Yeah.
Kelvin is metric. Metric is presented by Napoleon. Kelvin just sort of, again, starting at absolute zero makes sense.
Yeah.
But any measure of temperature is sort of arbitrary as opposed to.
That's true.
Yeah.
I guess this is correct that Celsius is not necessarily, it's not like all the other metric things. So I use meters instead of feet because like numbers that go into each other in tens are better than 12s and 5280s. But
you don't multiply by temperatures in the same way.
Yeah, but temperature multiplication is different than that.
Yeah.
So I guess the real answer is that I have to, when I publish this, it'll be required to be in, because the organizations that do the publishing are not terribly fond of imperial.
Yeah, no. Scientists use it, therefore you have to use it if you're a scientist.
So since Connor started this, the city has been doing stuff in the 3 years, in addition to the study. And in the last several months, maybe you've seen in the newspaper, there's been a subcommittee of the Parks and Rec Department formed to manage our springs, which is unprecedented. That's never been done. And then through that committee, they were able to historically designate these springs. So they will be protected. Once Connor gets his and helps the city with the mapping, there'll be different, same thing, red, yellow, green, where interactions can happen. So now, instead of just hoping that maybe CDOT doesn't build a new highway and that we don't lose any more springs, hopefully now through these protections we'll actually be able to maintain these springs. Our two oldest, Steamboat and Black Sulphur, I don't know if you're aware, they're very close to the railroad.
Yep.
So talk about human interaction. And the Black Sulphur is actually on Union Pacific land partially. So we're having some issues with ownership and how to regulate that. But for the first time in the spring's history, protections and steps are moving forward as best we can.
And if I can speak into that, we're on the Mineral Springs Committee.
Yes!
So the National Historical Designation is not quite there. We're definitely at the local. We're going to the state and then the national the next steps. But one example of kind of how we've started to protect them is that there is an overhead power line at Iron Spring, and they wanted to do some underground. They wanted to place that underground, which is great, except for we have a spring in the middle. And so what they've done with our committee, we said, no, you can't dig there. And so they've rethought their electrical line. So they're going to have two ends truncate, one going south, one going north. And so then the spring is now protected.
Cool.
So it's kind of a nice next step that we've been able to say, hold on a minute, rethink this. So
That's great news.
We got a couple more questions.
There are a lot of towns in Colorado with springs in the name. Have they gotten similar studies to the Steamboat Springs?
I was connected to the city of Steamboat and the Treaded Pioneers Museum by the Springs Foundation in Manitou Springs, where I did a very similar study. So Manitou has had a similar study done I'm not sure about the protections in Manitou. And then Glenwood Springs have also done a similar type study there. I'm trying to make it to all of them, so I'm trying to go to Pagosa's next.
Colorado Springs.
Colorado Springs, that's true, yep.
So which is the Lemonade Spring and why is it called that?
I was looking at the booklet and it had like the little quiz in the back, and I was like, oh, I don't know what. Was Soda Spring
The one in the gazebo, or what would be in the gazebo until the 1980s, had a, Marion can tell us, a high bubbly. It
Yeah,
had
it was very
carbonation, and
People
it's,
need
yes, the early pioneers would put in a tablespoon of sugar and some lemon, and it was the finest water. Like, I don't know what we drink
They
today.
always had a tin cup there.
And they kept a tin cup there, and people came from all over, and that's why the depot is so near our springs, because that was why people came, was to enjoy the health benefits
People
of.
stopped at the soda stream
Yes,
all the time. 'cause
it was,
right, and it was right next to the highway.
it was right next. Yes, so that's why. They mixed it with lemon, and it was delicious. And we don't get it today. Which we don't encourage drinking water anyway, ground.
Yeah, I love spring water. I would not recommend, having done a lot of detailed geochemistry on the springs of Steamboat, I would not recommend drinking that. I cannot make health, I guess I shouldn't say recommend, because I'm not allowed to make health recommendations, because I'm not USGS is non-regulatory. I would advise against.
Here you go. Any other questions?
To what extent did you do the thermal mapping up and downstream on the Yampa?
Yeah, that's a really good question. We went, let's see, probably, let me go back to the map because that'll be the best way to explain it. There's certainly more that could be done. So we went outside the extent of this map. So we went maybe a kilometer downstream and a kilometer upstream, but we did not go away from the river corridor.
Because there's quite a few others around Lithia Spring,
Yeah.
but you didn't track Lithia.
No, we had the sensor installed in Lithia, and we collected the samples of Lithia, but did not do the detailed mapping.
Okay.
of Lithia.
Let me speak really quick again. So School of Mines has had their geophysics camp up here for 2 years now. We're going on our 3rd year. And we are also trying to now get the geology field camp up here for at least a week. And one of the projects that I would love to have them do is to map where all the springs are. So if there's 10 of them around Lithia, we know there's one out in front of the power sports one because they're always having to sump pump that one out. And even if you go up on the house and ski jump area, there's one coming out the side right there. And so it would be fantastic to have data because we just don't know where they all are. Even though we have at least over 150 is what was published in the book. But it would be a great project for School of Mines Geology Field Camp to get up here. So I'm working on trying to get them up here.
Yeah, and one of our recommendations for potential follow-up studies would be to do thermal imaging from a drone, because that would. So we went along stayed along the river corridor because that's city property, and we're working with the city, so we're not allowed to go on private landowners. With a drone, you can see everything within the field of vision, so it gets around that constraint.
Wow.
Yep.
What's your best idea about why black sulfur is getting so much recharge when it's so close to Steamboat Spring?
Yeah,
There's that lateral fault that goes right through that whole area, and would that be of some sort of mapping tool to figure out what the recharge area is?
Yeah, exactly. So I think that black sulfur is probably coming, the flow path that black sulfur is located on, I think is probably off a shorter splay of that lateral fault that you can see there in the, I guess not a road cut, but the railroad cut, yeah. And Narcissus this is a good slide to be on this. So here's Narcissus Spring, which has no temperature. That's the one with almost no temperature change. So I think that is located along the primary upflow zone. That's the most direct conduit in this area from the geothermal reservoir. And then Steamboat is located right here. That's probably on, I would think, a subsidiary structure to the structure that Narcissus is on. And then Black Sulphur Spring is right here. So when we are doing this, we're kind of stepping to the northwest, and I think away from the primary conduit. Okay. And I think that Black Sulphur probably has seasonal or maybe continuous recharge of young groundwater along that same fault. So that fault might allow it to be almost a bidirectional exchange, in that there's deep water coming up along the fault, but maybe there's some shallow water circulating downward along the fault.
I was gonna say, the backside of that railroad grade
Yeah.
collects a lot of runoff.
Yeah.
I mean, there's cattails and everything as you go up towards House.
Yeah, which could be the source of the young groundwater.
Great. Well, thank you for your time and for coming to see us.